Hi, so in today's video we're doing optimization, which means we're trying to find like the maximum value or minimum value of a function, particularly a multivariable function. And so we're just going to do one problem, and I provided some formulas here. So the question is in black, so what we're trying to do is we're trying to find the critical points of this function x to the power 4 plus y to the power 4 minus 4xy. And then afterwards we want to use the second derivative test, and the second derivative test is the one formula here that I provided, and we want to determine whether it's a local maximum or local minimum or a saddle point. A saddle point in multivariable calculus is essentially a point that has both a maximum and minimum value. And if you think about the word saddle, it is like the horse, like the seat that you use when you ride a horse, for example. And in this picture, for example, it is like a saddle, and this is the point that is called the saddle point. And if you take a look, it can be both a maximum because here the curve is kind of going downwards if you continue on, but it can also be a minimum point because if we do the other side, it will be a parabola that's going upwards. So that's why it is called a saddle point. And to figure out whether the local max or minimum or saddle point, we use the second derivative test. But the first thing that we want to do is we want to find the critical points. So in single variable calculus, we learned that finding the critical points of a function, let's say fx, to find the critical point, we just need to take the derivative and then we set it equal to zero, to find the critical points. So in this case, it's the same thing, except we have multivariable calculus. So what we want to do is we learned previously how to take partial derivative, right, of fx and fy. If you don't know how to take partial derivatives, I recommend watching the previous video. So now let's actually try doing this problem. So first step is we want to find the partial derivative of fx and fy. Fx in this case, we want to derive with respect to x, so we treat y as a constant. So for our first value of x to the power 4, that would be 4x cubed. The y to the power 4 is a constant, so that disappears, and then we have negative 4xy, and we want to treat y as a constant. So when we have x by itself, then that would just cancel out, so our derivative would be 4y. On the other hand, for f of y, we do the same thing. Now we have x as a constant, so x to the power 4 will just cancel out, so our function would be 4y cubed minus 4x. And then the second step we want to do, remember, to find critical points, we have to set the derivative equals to 0. So we set both of this equal to 0. And essentially what we're trying to do here, the end goal of finding critical points, a critical point is basically a coordinate. So that means we want to find what x and y is. So you can treat this as like system of equations. So let's say if in this function we have y, so perhaps we can potentially isolate y. It can be done in different ways, but basically the end goal is you want to find x and y. So let's say if I move 4y to the other side, I get 4x cubed, and then y would then just be equal to x cubed. On the other hand, if I do the same thing here, we have 4y cubed equals to 4x, and x would be equal to y cubed. And then the second step is we can then plug these values back into the partial derivatives. So let's say if I were to say plug x, or let's say I use y cubed equals to x. So if I plug y cubed equals to x into the other function, so I'm using what I have here and I plug it into here. So if I plug it into fx, then I would get, so I want everything to be in terms of y, for example. I can potentially say, okay, so y y cubed. So if I take y cubed, then this side would be y cubed to the power of 3. So it'll be 3 times 3, which is 9. So it'll be y9 to the power of 9 minus 4y equals to 0. And we can try solving for y. And we can first factor out for y. So we get y8 minus 1 equals to 0. And in this case, we have two different, when you factor things out and it's equal to 0, this can be equal to 0 and this can be equal to 0. So we have 4y equals to 0, so y can be equal to 0. Or we can have y to the power of 8 minus 1 equals to 0. So y to the power of 8 equals to 1, meaning that y can be plus or minus 1. So we have three values for y. We have y equals to 0, y equals to 1, and y equals to negative 1. On the other hand, we can try plugging it now into this function. So this time we can plug this into this. So we want to plug x cubed equals to y into this. And we kind of have a similar thing here, except it's in terms of x. So it would be 4x to the power of 9 minus 4x equals to 0. And if I isolate everything, I should get x equals to 0 and x equals to plus or minus 1, kind of like the same here. So that gives us different points. So we have 0, 0, we have 1, 1, and we have negative 1, negative 1. So we have 3 different coordinates. And then the next step for optimization, this time, because we're dealing with multivariable, we're not completely done with the problem. So in multivariable, you also want to take fxy, because notice in the function or in the formula for the second derivative test, we want to know what fxy is and what fx and what fyy is. So we'll find that. So fxy is we are taking the derivative of fx, and now we do it in terms of y. So we have 4x cubed minus 4y, and we are trying to, so if you just think of this as, g, for example, this would be essentially g of y. So to find that, all we're trying to do is do what we have done before, and we derive with respect to y. So meaning, if we derive with respect to y, 4x cubed would be cancelled because that's a constant, and negative 4y, the derivative of that is just negative 4. And we also want to find what fxx is and what fyy is. So again, fxx would be basically gx, right? Just to make it easier to understand, we're taking the derivative of this and we take it again. So, but this time it's with respect to x, not y. So the negative 4y would cancel out because that's a constant, and the derivative of 4x cubed would just be 12x squared. And then for fyy, we're trying to take the derivative of fy with respect to y. So again, the negative 4x is gone because of a constant, and 4y cubed, the derivative of that is just 12y squared. And when we take the second derivative, we want to also set it equal to 0 because we're trying to optimize it. And when we optimize it, we get y would just be equal to 0, and then x would just be equal to 0. So it just proves the point that we have x equals to 0 and y equals to 0, but that is not too important in terms of setting it equal to 0. So we actually don't have to do it. It's just to help us understand. But the most important part is know what fxx, what fyy, and what fxy is. Because now the second step we want to do is, now that we have the critical points, we want to figure out if these points are a local maximum or minimum or saddle point, because let's say I have 0, 0, and then I have 1, and I have -1, -1. You want to know which one is a maximum or minimum. This could be a maximum, or it could be a saddle point, or this could be a minimum, or it could be a maximum. So we want to basically determine what these points mean, because we want to know if it's a max or min or saddle point. So then we would use this formula that we're given, and then we plug each of the point in and see if it's positive or negative, or the discriminant is equal to 0 or less than 0. So for our first point, we can test with 0, 0. So maybe just to make it easier, I'll actually copy and paste this down here. Right. So for our first point, we have 0, 0. And to find the discriminant, we're just trying to plug in all the values here at 0, 0. So the discriminant at that point would be fxx at 0, 0. And fxx at 0, 0, which means that x would be equal to 0, so it would just be 0, times fyy of 0, 0, that would also be 0. Actually, I'll just, how about for our first point, I will just make it, I'll just explain it by writing step by step. So what we're trying to do is we plug in the values, 0, 0, and all we're trying to do is we're trying to see if the whole thing is positive or negative, and specifically for fxx, we want to see if that is greater than 0 or less than 0. So we have all these different conclusions that we can make. But first of all, let's just break this down. We have fxx at 0, 0, and we know fxx is 12x squared. So 12x squared, this is without plugging the points, so just to make it easier to understand, we have that, and then minus fxy squared, which is -4, so -4 squared. And so now at 0, 0, so x is going to be 0, y is going to be 0, so it's just going to be 0 times 0 minus 4 times 4 is just 16, so we have minus 16. And if we take a look at this whole thing is equal to -16, and we see that the discriminant is overall a negative value, and here we have this conclusion here. So because this is less than 0, that means that the point 0, 0 is a saddle point. So that's kind of how it looks like. Now I'm gonna speed it up a little bit and do for the point 1, 1. So that's the discriminant at fxx at 1, 1. Now I want to take a look if that is greater than 0 or less than 0. So let's take a look. So fxx at 1, 1. So we have fxx at 1, 1. That just means that, 1 squared is just 1. So we have 12 as fxx. And then for fy, we have 12y squared, and 1 squared is just 1, so it'll just be 12. And then since fxy squared at 1, 1, we know fxy is just a -4, so it doesn't really matter if we plug it in or not, it'll still be -16. And if we think about this, 12 times 12 is a big number, so the discriminant is definitely greater than 0. And in this case, we have two scenarios. So if the discriminant is greater than 0, the next step we want to determine is we want to see if fxx at 1, 1 is greater than 0 or less than 0. We set that fxx at 1, 1 is 12, which means that it is greater than 0. So this means that it is a local minimum, because fxx is greater than 0. fxx at 1, 1 is greater than 0. And then last but not least, with our final point that we want to test out, it is -1, -1. So to do that, we find the discriminant at -1, -1. fxx at -1, -1 is just 12 because we're squaring it, so it'll just be 12. And the same goes for 12y squared, because 12 times -1 squared is just 12. And then again, we have the -16 because the point does not do anything to it. So we see that this whole thing is greater. It is also greater than 0. And we also want to determine if xxx at -1, -1 is also greater than 0 or less than 0. Again, we said that it's 12, which is greater than 0. So we also have a local minimum at the point -1, -1. And so that's how you do this problem of optimization, and how to determine if the points are local minimum, maximum, or a saddle point. Thanks for watching.